So when you have tall buildings, when we make models, we have to have a good understanding of the behavior. So when you have a very tall building, the building can twist. And what are the repercussions of twisting of the building on individual elements like beams, columns, and so on? Can they be subject to torsional moments? The answer is no. Even if the building twists, individual members will not be subject to torsional moments. The reason is we know torsional moments have to be resisted by concrete and reinforcement, and reinforced concrete sections are not very good in resisting torsion. So as steel sections. So if you are having steel columns or concrete beams or steel beams, they are not very good in resisting twisting. And if you are going to have twisting, then we have to be careful. And then again, the main elements will bend only about one axis. They will not have biaxial bend. And columns will carry mainly axial loads, and when you have very large columns, the moments acting on the columns will not have much influence. And concrete walls will be very strong in carrying in-plane loads, but out of plane, they are not very strong. So if you are expecting some out of plane loads on walls, then better to go for thicknesses like 300 or 350 millimeters, so that the effect of out of plane movements will be very negligible. And slabs can carry flexure and they can provide in-plane stiffness, but slabs cannot make beams stronger. There's a misconception among new engineers that when they are modeling, they model the slab and the beam all together, and they think slabs can make beams stronger. It's a wrong perception. And you can get very wrong results by making such false assumptions. So that's why, you have to learn proper theories of finite element modeling, and also FEM programming when you are students, so that you will have a thorough understanding of the way that the FEM programs have been written, and that will give you a good understanding of how to do the modeling. And we call it art of modeling rather than science of modeling. And although these rules are there, there can be exceptions. So we must identify them early. And then there are so many other behaviors, because we have been talking about static behavior, but there are dynamic behaviors. So when it comes to designing, we have to see what a three-dimensional model can give us. A three-dimensional model can give us natural period of vibration of the building, and we can also get earthquake analysis and wind analysis results, good results from the 3D model, and then we can also get loads on columns, diagrids, and so on. And also, if we are having transfer plates, then again we can get loads, bending moments, shear forces on transfer plates. But the 3D model will not tell us anything about the slab design. And 3D model or results cannot be used for beam design, because we are not getting pattern loading that the codes recommend us to consider when you are designing beams. So when you make a 3D model of a structure, you can have walls, transfer plates, pile caps, and when you are designing columns, you can have load reduction factors, and they are all allowed in both Eurocodes as well as BS codes. But the time has come for us to stop using BS codes, but to move fully for Eurocodes. And we hope very shortly CEDA will issue a directive saying that all building designs in Sri Lanka and any other structure design in Sri Lanka should be carried out according to Eurocodes. And if you look at Road Development Authority, you will already see now Road Development Authority requires all their designs to be done according to Eurocodes. So Road Development Authority has already moved, and we hope that CEDA will take correct action shortly, so that we will be forced to use Eurocodes for all the structural designs, because we have not seen any advancement of British codes in the last 12 years. Since 2010, nothing has been done about British codes, which means, if you are using British codes, then you are using fairly outdated codes, and you must not be using British codes anymore. We must firmly move to Eurocodes, because Eurocodes allow us to have national annexures. And if you cannot have a national annexure immediately, we can always look for the national annexure of UK, because they are also having temperate climatic conditions and they are having warm summers. So because of that reason, most of the rules that they use in England can be applied in Sri Lankan conditions as well, because we are also having mild conditions. We are not having extreme desert conditions. So there's nothing wrong in using British standards or British national annexures of Eurocode in Sri Lankan conditions, but it's always good to have our own national annexure, so that we'll be able to have additional rules. And then when you are doing a model, here you can see a structure where below the in the car park levels we have beams and columns, and whereas above the car park levels we have apartments, and for apartments we have used walls. And then when you're in the car park level, you can analyze these structures, beams. And when you're analyzing a beam, one of the assumptions that we make is the beam is supported by a column, and column does not settle. Now that type of assumptions would be pretty good for 2-story, 3-story, 4-story type buildings, but when it comes to tall buildings, you can have differential shortening of columns, and differential shortening means different adjacent columns can shorten by different amounts due to the variable axial forces acting on them. And if that is going to happen, we should not say, we are going to have a simplified model like this and we are going to have pattern loading. We must also look at it in a little more logical manner, because we are not including the wind loads in such a simplified analysis. And even if you have included the simple wind loads, still you'll find that the differential shortening should be given some consideration. So when you are designing, you will look at the bending moments, but you'll also consider the possibility that some plastic hinges forming close to the columns that can increase the span moment. So general tendency is, if I am doing designs, I generally tend to over design the beam section in the span, but I do not over design the beam section at the support. So the reason is all the codes allow certain degree of moment redistribution at the columns. So because of that reason, I do not really worry about the bending moment at the column, and also the effect of bending moment at the column due to the differential shortening. That also I will not worry too much. But to take account of all these unforeseen effects, I will over design the beam in the span section by about 10-15% or sometimes 20%. And then when it comes to the design of columns, you can always use the tributary area and calculate the loads on columns. And then beams also, you can have different sizes. So basically, it's possible to select beams, columns, and all the structural members in a tall building also by using simple calculations. But there's a big difference between a 2-story building and a 40-story building. In a 40-story building, we must, in addition to doing the calculation, we should take some assessment of risks. And risk assessment is a very good initiative. If you should train your mind to always be inquisitive and ask questions. This building is very different to a 2-story building, And I have designed 2-story buildings, but today I'm designing a 40-story building. What can go wrong in a 40-story building that you do not get in a 2-story building? That you have to always think about it. And then when you are designing tall buildings, again we have another challenge. Just because we have risk, we cannot be over-designed. We have to be accurate with our designs. So how we optimize the building is we look at the structure elements that cannot go wrong. And we also look at the elements that things can go wrong. So if you take a normal building with beams, slabs, columns, slabs cannot go wrong. So we optimize the slabs. In beams cannot go wrong at the support, but beams can go wrong in the span. So we over-design the span, but not the support. Then we also look at shear carefully, and also we also try and see whether torsion occurs. And then when it comes to slabs, we optimize as much as possible. But when it comes to columns in the top part of the building, not a big problem, but in the bottom part of the building, we'll be very careful with the columns, because if anything goes wrong with a column in the bottom part of the structure, things can go wrong drastically. And we have seen one building collapsing in Miami, and nearly 100 people have died. So that type of collapses are totally unacceptable. And that collapse would have occurred due to the engineers underestimating the effects of construction sequence on the transplants. So I think that is the final finding of the teams. And so basically, when you are designing, you have to do a risk assessment, see which element can fail, and any element that you think has a tendency to fail, you will provide extra reinforcement and extra moment capacity and extra shear capacity. And if you think there's any element that can be subjected to axial shortening and induce plastic hinges, then rather than using very large diameter bars, you will use a number of small diameter bars so that the cracks will occur, but nobody will see the cracks. So likewise, you have to get a deep understanding of the behavior of the structure and then do the detailing rather than blindly doing the detailing just by looking at the reinforcement area is 880. Then I can just provide 2 bars of 25 diameter, because each 25 diameter bar is 490 millimeter square. That type of calculations are not acceptable. You have to always see now what are the spacing, maximum spacing between bars, or whether it's better to have bars at a closer spacing than a larger spacing. If the area is 880, then you might see whether it's better to use 3 numbers of 20 millimeter bars than using 2 numbers of 25 millimeter bars. Not to say steel, but when you have 3 numbers of 25 millimeter bars, the crack widths will be smaller. So even if something goes wrong, still nobody will see any cracks, and no cracks means no investigation, nothing to worry. So likewise, you have to think about it. And when it comes to columns, always, you will see the possibility of columns failing due to providing too little reinforcement. And you will do a risk analysis and then again see which level that you have to provide special additional reinforcement. And when it comes to concrete, also the same. And it's always good to use high strength concrete where necessary. But if you are using large sections like in a transplant, that means the structure is not optimized. So in such a situation, there's no need to go for high strength concrete for transplants because the structure is not optimized. We are using huge sections because the load transfer needs huge sections. And then when you are designing, again, you have to be very careful. And if you look at this particular column, you can see this is M33 and this is M22. Generally, we look at M33 all the time, but in this particular case, M22 is massive. So you have to always look at all the different moments, forces, every moment. You should not think, okay, I always look at M33 and I'm going to look at only that in the design. You must always look at all the different moments. And you can see when you are modeling in Sri Lankan conditions, it's always possible to model the structure, superstructure with substructure. And this kind of modeling is totally acceptable because we are having bedrock. We are having bedrock. So you can model the superstructure, substructure all together, and you can get accurate results. And also you might get situations where the transfer plates are there. And now you can see some of these walls are not on the beam, center of the beam. Some of these walls are on the side of the wall. And here you can see again, you can see some of these walls are not on the beam, they are away from the beam. So which means some of these large beams can be subject to torsional moments. And if you look at some of these locations, beam locations, you will see that they are not on the center of the beam. The wall is on the side of the beam. That means the beam can be subject to torsional moments in addition to the bending moments. And to take account of that, you have to design the beams for torsion, and most of the time we don't design beams for torsion, but when it comes to transfer plates, you have to design transfer plates for moments. So you can get torsional moments, additional reinforcement, and sometimes you will find the shear links are not 10 millimeter now, they are of 25 millimeter diameter bars. These shear links are not shear links, they are torsional links. So likewise, you have to develop good understanding of all different, because most of the time we have seen students learn only to design for bending and shear. You must also learn how to design for torsion, and you must use those. And then when you have massive sections, we have a different problem, and that we call delayed ettringite formation. That also should be paid attention. And to help you to sort this out, we have developed a set of curves that will help you to predict the maximum temperature that is reached by different types of concrete mixers. And you can download this particular paper just by typing M.T.R. Jayasinghe DE and DEF, delayed ettringite formation, and you can download this paper, read the paper. We have solved one of the biggest problems that all the engineers faced. Now these days, you can easily use this paper and predict the go beyond 70, but 70 is given as the margin, and you can easily see how the concrete mixers you select will give maximum temperatures and whether they are over 70 or below 70. And then we talked about transplates, and we have so many buildings in Sri Lanka having transplates. This Keskat having a transplate here, and then we have to design them very carefully. And sometimes, they cannot be cast in one operation. You have to cast them in two operations, where first you design the first 400 or 150 millimeter thick slab, and to carry the weight of the concrete above, because it's very difficult to get formwork. And this is another example, classic example of having a transfer plate at 10th floor. This Cinnamon Red Hotel. And when you enter at this level, then you have to go to 7th floor. And at the top of 7th floor, you get restaurant. And then above all that, you get a transfer plate at the 10th floor level. And to cast a transfer plate at 10th floor level, the biggest problem is the weight. And we solved that problem by going for a cellular raft, cellular transfer plate, where we cast the bottom part of the transfer plate first, and then we formed the voids, and then we cast concrete around it. So that way we saved a huge amount of money. And I think the saving in that particular building from the original design had been about 200 million rupees. And that made it a profitable venture for Sankhya Lanka, the owner of the building. And then when it comes to piling, again, we have rules of thumb. For different pile diameters, we have different capacities. But these are for normal situations. But when it comes to super tall buildings or large buildings, that type of simple pile calculations are not applicable. You have to go deep into it, and you have to see how much socketing, extra socketing is needed to deal with skill friction. And again, using the ICTAD guidelines is again too restrictive. You cannot rely on ICTAD guidelines. So what you do is you will go for pile load testing, PDA testing, and maintain load testing. And in a normal guideline for 1,200 millimeter pile is 6,500 kilonewtons. But in Altair, we use 11,000 kilonewtons for 1,200 piles, and 1,500 piles we use a normal guideline like 10,000 to 10,500 kilonewtons, but in Altair we use 17,000 kilonewtons. And when the structural engineer said, I want to use 17,000 kilonewtons for 1,500 millimeter pile, the geotechnical engineers did not like it very much, but we said, unless we can use 17,000, we cannot have such a tall building, whether you like or not. We are going to do load testing and maintain load testing and PDA testing, and we are going to decide the pile load carrying capacity based on those testing rather than the predictions based on theories. And we found that our guess was better, that the maintain load testing and PDA testing proved that our guess of 70,000 is actually proper than using very low values. And then again, you have to think of piles in weak soil conditions, the lateral stability of piles, and for that again, we can use spring methods, and we teach these methods for geotechnical engineers even in the final years of Mortua. Those who are taking large structures, they learn those theories. And for their comprehensive design projects, they use not only their own lecture note, they use even the MSc notes, because in comprehensive design projects, we expect students to go deep into the subjects than finishing at very shallow levels. And you can see, you can have springs representing the soil conditions and so on. So a lot of information, a lot of things that you have to do that you do not generally do for a 5-story, 6-story building when it comes to tall buildings. But these are not super tall buildings. These are tall buildings, something like 20, 30, 40 story range.